Hello everyone, how are you? I hope you're doing well. I hope that this is not the way we are communicating and we are talking over a live setting and interacting with one another, but just in case, I'm recording this video. My name is Mehdi Behrouzi. I'm an assistant professor at Northeastern University in Boston, Massachusetts. And let me share my presentation here and we'll go from there. And at the end of this presentation, on the last slide, I have my emails and my collaborator's email, and you can send us emails with your questions. If you have any, I would be more than happy to answer those questions. I want to talk about crowdsourced delivery with drones in last mile logistics. As you know, the last mile, this is a joint work with my doctoral student, Dinghao Ma. And as you know, the last mile delivery operation is the most expensive part of it, and as based on some estimates, is as much as like maybe 50% or more of the total delivery cost. Here we want to use the concept of sharing economy and combine it with the last mile delivery and see whether we can design a more efficient system. Of course, there have been a number of works on crowdsourced delivery in the last mile delivery operation, but here specifically we want to study a system that is performed through sharing economy platforms and being handled by drone operators, which makes a difference between drones and other agents. So as you see in the picture on the left, there's a customer who makes an order through one of the sharing economy platforms or applications. The warehouse or the nearest distribution center receives that order from that customer and maybe other customers, combines them and pulls them into the truck. And the truck takes all of those packages and brings to a neighborhood with a cluster of customers. And from here, instead of delivering the packages one by one to the residential addresses, it passes that order to, or those orders to crowdsource agents such as drivers, bikers, walkers, and drone operators. So they come to this stopping point of the truck. We call it cluster center. And the drones fly from their base to this cluster center. They pick up a package, deliver it to the customer, and come back to that drone base. And we want to study this problem and see if this would create a more efficient system. And of course, we have some assumptions, just like any other optimization or operations research problem. Here we are assuming that each drone can carry only one item at a time. The charging time is almost zero, equal to replacing the battery. There is no weight limit for a drone to carry the package. The capacity limit is on the number, not on the weight. The speed of drones are assumed to be 3 times that of the truck. And if there is a customer that is out of reach of drones, truck would serve it and or serve all of those customer nodes that are out of reach of the drones. And drone has to return to the base after each delivery, and each drone base launches only one drone. Of course, some of these assumptions can be generalized very easily, and some others might be a little bit more intricate, but we believe that all of them are doable. So in order to understand the problem better and understand the problem formulation better, we first look into one of those neighborhoods, one of those clusters, and see how we can model the problem there in one cluster. Here, our goal is to minimize the total time that it takes to serve all the customers in that cluster. And this is equivalent to the minimizing of make span, or maximum time that it takes to serve all of the customers. And We define a customer set C, a drone set D. We would only have one truck node in one center, and the dij would show the length of the route between I and j, but it is defined in a way that I is a drone node and j is the customer node. So it's the length of the tour that goes from I to the center O, and then to the customer j, and then coming back to the base I. Cij is the time equivalent of that distance. Vd is the speed of the drone, and L is the longest distance that the drone can travel without changing battery. Xij is the binary decision variable if customer J is being served by drone I through the center O. And Qi is the total time that the drone is traveling. And capital Q is the maximum time by all drones or our make span. So this is our problem formulation for one center. We are minimizing the make span. All the customers have to be served by have to be served by the drone. This has to be J for all J, and the total distance of the drone has to be less than L, and the total time that the drone it takes for the drone to serve all the customers in that neighborhood is registered in Qi, and capital Q finds the maximum time for all drones. Now we can generalize this to the general problem in which we have multiple clusters, and the truck should go from one cluster to another cluster. And if there's any customers in between that are not within the reach of any drone, then all of those customers have to be served by the truck. So the new parameter here, the new variable or parameter here is dpp prime, which is the distance that takes truck to go between the customer point P and customer point P prime. CPP prime is its time equivalent, and DIJP is the length of the route to serve customer J by the drone at node I through the center at node P. CIJP is its time equivalent, and L is the longest distance, and N is a big number. The binary decision variable YP is 1 when we serve point P with a truck, and XIJP is the point is a binary decision variable for serving customer J by the drone at node I through the center P. QIP is the total time traveled by drone P at node I, and QP is the maximum time spent by all drones in the cluster P. And gamma PP prime is the binary decision variable if the truck traverses the path PP prime. UP is a dummy variable for subtool elimination constraint, and delta and epsilon PP prime are binary decision variable for linearization. So here our objective function is again to minimize total time of serving all the customers. The first term is the total time that it takes for the truck to go between the points P and P prime in the customer nodes. Of course, not all customer nodes are going to be served by the truck. Some of them are going to be served by the drone, and that total time is being calculated in the second term. The first constraint ensures that at least one customer node is being used as the cluster center. Constraint 2 ensures that all the customers in the customer nodes are being served either by the drones or by the truck. And constraint 3 ensures that the uh, customers can be served only through the center P if that center is being visited by the truck. And constraint 4 ensures that we don't overreach, we don't overfly the drone beyond its limited battery. Constraint 5 ensures that or calculates the time that it takes for the drone at node I that is being assigned to node P to serve all of the customers in that cluster. And constraint 6 finds the total time or the maximum time that is being taken by all the drones to serve the customers in that cluster. Constraints 7 to 9 are the TSP constraints. And as you see, constraints 7 and 8 have some nonlinear terms. To linearize them, we'll define 2 new variables and 6 new constraints and modify constraints 7 and 8. So about the algorithm, we designed a heuristic approach in 4 steps. In the first step, we run a k-medians clustering algorithm to cluster all of the customer nodes into a number of clusters that makes it feasible to visit all of them within radius L4 of the cluster center. And L4 is to make sure that the drone can fly to go to the base, to the center, and then from there to the customer, and then come back that distance. Then in the second step, we partition all of the nodes using Voronoi diagram. We assign the points to the cluster centers using this partitioning scheme. And then we run a taboo search algorithm to solve the subproblem in each cluster. That's our one center problem. And finally, in step 4, we would try to solve the truck path using the famous TSP algorithm LKH. Here you see the simulation for some random instances run by our algorithm on the left. You see the partitioning scheme is the Voronoi diagram, and the points assigned to the cluster centers, and the star points are the drone nodes that are flying over and serving the customers. On the right, we solve some random instances with our optimization model over different values of L. And as you see, as the value of L changes, our solution changes towards more use of the truck or more use of the drone. We compared our algorithm's performance with the model over an example with 40 customers and 20 drone nodes with different values of L. As you see, the time comparison, our algorithm beats the optimization model. Is much faster, almost 6 seconds compared to 140 seconds. And on the optimality gap, all of the instances are being solved within 2% optimality gap, with the average being just 0.63%. And we compared this with the traditional truck delivery model, our algorithm with the truck delivery model, which is a pure TSP, and this shows almost 15% improvement in the efficiency of the last mile delivery. So for the sake of time, I'll be quick on this conclusion part. We designed a new problem, we defined a new problem, we designed the optimization model for it for the last mile delivery system, and we tried to design a new and more efficient last mile delivery system that takes into advantage the sharing economy concepts. and we devised a new heuristic algorithm for it. We could compare it with a coordinated delivery system that the drones are being controlled by the truck driver, but that would require a number of other factors, such as the number of available drones in our system versus the other one, and the capacity, speed, etc. And we would like to take a look into that into the future work, and there are a number of other things that we could take a look into in the future work, such as capacity of the drone, weight capacity, combination of that with crowdsourced drivers, etc. Thank you very much, and I will be more than happy to take questions through email.